Assalamualaikum. Good day, everyone. My name is Isnaeni from Research Center for Physics LIPI, Indonesia. I would like to thanks to ISMM2020 organizer for giving me time to present my work entitled Simulation Study of Size and Aggregation Effect on Colorimetric Spherical Gold Nanoparticles. This is my presentation outline from introduction until summary. Let me start by saying that gold nanoparticles are very applicable due to plasmon effect. The appearance color of colloidal gold nanoparticles depends on size and aggregation. We know that the top-down and bottom-up procedures can be used to synthesize gold nanoparticles. These procedures create not only monodispersed gold nanoparticle, which is good for most applications, but also aggregated gold nanoparticle, which is also useful for some specific application. Usually, we utilize transmission electron microscope (TEM) to check size, monodispersion, and aggregation of synthesized gold nanoparticles. However, TEM is expensive and time-consuming. The challenge is to create simple technique to monitor synthesized gold nanoparticles. Colorimetric could be the answer, since color of colloidal gold nanoparticles describe their size and aggregation. Until now, there is no standard procedure to do this colorimetric technique. Therefore, in this study, we computationally studied the colorimetric of gold nanoparticles due to size and aggregation. To display the true colorimetric results, we use color diagram CIE1931. We assume that this work can produce simple colorimetric technique to observe colloidal gold nanoparticle. In order to simulate colloidal gold nanoparticles, I use MNPBEM toolbox from Hohenester from University of Graz, Germany. This free toolbox utilizes boundary element methods to simulate extinction cross-section curve of any given size, shape, and configuration of gold nanoparticles. From this curve, we calculated the appearance or color and display it using CIE 1931 color diagram. We simulated single gold nanoparticles which represent monodispersed configuration and triangle and line arrangement which represent aggregation configuration for a particle size from 5 nanometer until 200 nanometers. Let me tell you how I can get predicted color in this work. The simulated curve, the black curve in the left figure, was then converted into transmission and reflectance spectrum, the blue curve. In practice, this reflection and transmission are what we can see by our eyes. This curve was then used to calculate color coordinates using color matching function of CIE 1931. This is a common procedural technique for displaying color using CIE 1931 color diagram. Thus, we can plot the color coordinates in the color diagram. Every color coordinates x, y describes specific color. This is a simple colorimetric standard. First, I will show you the result of spherical single gold nanoparticle simulation from 5 nanometer until 200 nanometer. We can see the extinction curve consists of absorbance and scattering peaks for larger size of gold. The calculated color coordinates are plotted in the color diagram. we can see that color of monodispersed gold nanoparticle change from red to purple to blue when the size of gold changes from small to medium to big. The middle photo is real appearance of 30 nanometer gold nanoparticle that we synthesize using laser ablation technique. This color change agrees with some experimental results. The extension curve changes when we use aggregation configuration. This is example of 30 nanometer gold nanoparticle with 3 different configurations. Monodispersed gold nanoparticles, the black extension curve, give red color appearance, dot 1p on the left figure. Triangle and line aggregation produce different extension curves, the red and blue curve respectively. This aggregation of gold become purple, denoted by point 3pt and 3pl. This is the overall simulation prediction of monodisperse, triangle aggregation, and line aggregation of gold nanoparticles from 5 nanometer until 200 nanometers. This is a little bit complicated, so I will describe it in detail. I will discuss small particle, 10 nanometer gold, medium particles, 80 and 130 gold nanoparticle, and large particle, 200 nanometer gold. On the left figure, we can see that the small 10 nanometer gold nanoparticle produce red color, and the color changes into purple when the particles are aggregated. The medium size of gold, 80 nanometers on the right figure, the color changes from reddish purple for monodispersed gold nanoparticle to bluish color when the particles are aggregated. This color change is mostly due to change and additional scattering peak on extinction curves. Mostly, the scattering is in longer wavelength or red color. Thus, the appearance color that we can see by our eyes is blue. A little large size 130 nanometer gold nanoparticle, left figure, shows the color change from purple for monodispersed gold to bluish color for aggregated gold. However, the large size of gold, 200 nanometer, in the right figure describes opposite trend. The color of monodispersed gold, blue color, changes to purple when the particles are aggregated, denoted by point 3pt and 3pl. In summary, the simulation of monodispersed and aggregation of gold nanoparticle from 5 until 200 nanometer can be simulated and further calculated and displayed in color diagram CIE 1931 to observe color change due to size, monodispersion, and aggregation configurations. Due to aggregation, the color of small gold nanoparticle become purple. The color of medium-sized gold nanoparticle become blue, but the color of large gold nanoparticle become purple. This result can be a new and simple colorimetric procedure to monitor synthesized gold nanoparticle. I welcome for any feedback and comment. Thank you very much for your attention.